Kia ora koutou. I'd like to thank the organisers of the Architecture Science Association conference for this year for inviting me to give this presentation. It's given me the opportunity to reflect on 40 years as a physicist conducting research in a school of architecture. I've entitled it People and Buildings because it seems to me to be the thread that links the nearly 40 years of my career. I'm sure this video was an attempt by TV3 to collect a news bulletin filler with an entertaining clip of people's jackets and skirts being blown about by the wind, but they captured something else altogether. What you saw in the video was predicted by the wind tunnel testing done for the developer of this building. We have wind regulations in Wellington designed to signal these issues. If the wind tunnel test shows that a building may cause a significant problem, then the building is normally greatly modified. This building was eventually given resource consent after submission of a third opinion. The wind tunnel test and the Wellington City Wind Advisor agreed design changes were necessary. The opinion stated almost any building of substance constructed on the site is likely to have a similar effect, which is what the wind tunnel test showed. Less substance was needed. I understand the developer's desire to overrule this initial environmental impact assessment. I presume their rule of thumb estimate of the value of the site will have been based on the height limit for the area and the site area itself. Multiply the two together to get the volume that you see in front of you. However, the video illustrates the problem of application of such a simplistic rule of thumb. The height limit is a crude urban design tool intended to reduce adverse effects on the local environment, such as shade, wind, need for resources such as drains and so forth. Unfortunately, following this crude rule of thumb and not the detailed wind analysis leaves us with a problem for at least the next 50 years. This is a video of Midland Park in Wellington in May 2007. You can see the people in this video mostly choosing to sit in the sun because it was a cool day. They're plotting the sun's movement across the site by where they sit. Another paper in this conference, presented by Kasun Pereira, a PhD student of mine, has taken this 2007 study and extended it. He is demonstrating that conventional physiology-based indices of external comfort that combine the obvious measures of wind, sun, and temperature are unreliable indicators of people's preferences in the real world. These indices of comfort appear sophisticated, but are little better than rules of thumb because they ignore people's preferences and behavior. The issue of performance indices and what people want arises also when we look at light. These early 1990s images on the left are of the Museum of Modern Art in San Francisco. Only the last of the three pictures, the one with the trees in it, is of reality. The other two are renders. Clearly, we've been able to model light like this accurately and to represent what a building could look like accurately for over 30 years. Instead, in our code compliance and our design tools, we typically have very crude measures. So people end up suffering. Instead, we have very crude measures of things like daylight factor for code compliance and for use in design. One result is people suffer in their apartments. Crystal Stewart's work 12 years ago measured daylight in apartments and demonstrated 50% of them didn't comply with the minimum 30 lux on the floor at the rear of the living spaces as required by the building code. We can do better. No one has asked, is this what apartment dwellers want? Crystal used climate-based daylight modeling to develop a simple compliance tool which would use a few simple site-relevant measures to identify the risks of non-compliance with the building code. We've had her risk-checking tool available online for the past 2.5 years. The plan is not to avoid detailed analysis, but to ensure it's only done when needed. I do, however, need to point out that current guides as to how to do climate-based daylight modeling typically focus on office daylight That is illumination on a desktop, not something that relates to how people live in buildings. Akli Anibi Tabasi has been looking at the broad issue of indoor environmental quality in school classrooms. In his work, we've noticed that while there are minimum standards for temperature and light, in acoustics there is the simplistic rule of thumb measurement of the reverberation time and a maximum intrusion of background noise. Earlier work by Sarah Leggett has shown understanding noise in classrooms is not a simple rule of thumb issue. She looked at 10 case study classrooms, choosing multi-teacher and single-teacher classrooms, as you can see from the first two columns on the left. Apart from the number of students, the biggest single difference between classrooms turned out to be the carpet, with or without soft underlay. Sarah undertook an ingenious process of asking the students themselves to assess the acoustics of their classrooms. She had them mark up plans from where it was noisy or quiet, and in this case where it was hard to hear the teacher's instructions. And then she overlaid them to get a frequency chart, as is highlighted here. At first glance, this is a clear win for the cellular single teacher classroom at the bottom. But if instead of looking at the two-teacher classroom at the top, we look at another two-teacher classroom of the same size in the same school, then the result is much more similar between the types of classrooms. Rather than rules of thumb about reverberation times and sound levels, what turned out to be most important lesson for us about acoustics in classrooms was Sarah's observations. This is from Sarah's notes in one of those two-teacher classrooms. If I go back to my beginnings as a researcher in building science, I was involved in a survey with George Baird, looking at energy use patterns in commercial buildings in Wellington, surveying 1,000 buildings in the central business district. We reported this, as I recall, in a 1981 architecture science conference. We measured the model on the right-hand side here because LiDAR and other data wasn't available at the time. We obtained dimensions of the building, the volume, the floor area, the percentage of glazing, and the nature of the opaque skin. This was much easier than walking around the streets trying to estimate these values. We also obtained every single oil, gas, and electricity bill for every single commercial premise in the city. What we found, to our initial surprise, was that physical parameters were less important than what people were doing in the building. Many years later, with the assistance of brands, we again studied commercial buildings. This is Tavis Criswell-World's study of optimum building form in post-earthquake Christchurch. Tavis modelled the wind pressures that drive ventilation in a range of different proportions of building form, mostly focused on the scale of laneway beside the buildings that would let in light and air. The exercise established that laneways could improve energy performance by improving the ability to get daylight and fresh air through those openable windows. If you followed the central Paris courtyard model, you could increase that energy performance even more at the cost of some net lettable area. However, the most important part of this study wasn't the energy use, it was looking at what it's like to be in the buildings. We demonstrated that there were real opportunities, even with a relatively narrow laneway, to get a very good distribution of daylight across the floor plate, as the near 100% daylight availability for two of the design options in the left graph demonstrates. We also showed that some designs of office buildings would almost always reach a comfortable temperature without any heating, ventilating, or air conditioning whatsoever, as shown in the right-hand side graph by the large green parts of the bars measuring the proportion of the year in a comfort zone. You, of course, needed to operate the operable windows to control the indoor temperature. Sean Corey, a PhD student, took a very different approach. He looked at this range of energy strategies in all the commercial buildings in the country, that is the existing commercial buildings. He had, unlike standard exercises of this type, instead of looking at some kind of prototypical building, he looked at real buildings whose energy performance data had been collected by the brand's Bees study. He calibrated his buildings against this measured data, and then he applied each of these strategies in turn. So it started off with a breakdown of the total energy use in office, retail, and mixed buildings across the country and by region. And he was able to show, if you applied one of these strategies, how much energy you would save. Not a lot. But if we applied all the energy conservation measures together, we could get a significant reduction. Even better, we only need to apply this reduction to a tiny fraction, 1,200 of the nearly 30,000 commercial, office and retail buildings in the country, in order to get at least 50% of these targeted energy savings. If we go back to our 1981 paper referenced earlier, when you run computer models of buildings, the performance is not normally as variable from one building to the next as happens in reality, because you're not modeling how people actually use the buildings. So the Christchurch buildings were very much prototypical. Sian's study of the commercial buildings in New Zealand was very much based on actual energy use in buildings, so we got a variability in the sample, but not variability of each building moved from one location to another. We took that sample and multiplied it up. So the most important parameter we're not modeling or recognizing is that different users manage the use of buildings in very different ways. Just as a footnote to this, I should add another irony. In that 1981 Anzaska paper, we also lamented the inadequacy of performance criteria and indices. I believe 30 years later, that lament remains valid. Back in 1990, I was keen to promote the then fashionable concepts of passive solar. In 1990, I wrote, with the help of another graduate student, a passive solar design and passive solar construction guide. Much of that early work in the field focused on trom walls and some artificial differentiation between so-called active and passive. I'm sure this diagram doesn't need explanation to anybody. The focus was on how energy might be saved. Problem was, we face a bunch of presumptions about how the world works in terms of mass, insulation, and glass. In between 2001 and 2010, we also wrote a guide to good practice with the Standards Association. We had some argy-bargy with the people who are trying to defend the role of mass in the thermal performance of buildings, and we're worried that our best practice might set the guidelines for what would happen next in the building code. Eventually, we only wrote this document about lightweight timber buildings, not about concrete ones. However, I suggest we should revisit this approach and should consider the philosophy of listing a guide with better and best practice building design features again today. They could, as happened prior to the 2009 change in the thermal performance specification, signal the next step change in the building code insulation minimum. They could even, in a different context, point to a daylight design best practice. Meanwhile, market leaders could use this prescriptive standard in specifying the performance of their buildings to builders and clients very simply by reference to this document. In a study of thermal bridging and modeling for brands, we found typical code calculation specified proportions of timber and walls were half the real amount of timber. This graph shows the reality we found when we went beyond simplistic heat loss rules of thumb. We took real data on the dimensions and reported R values, plus the measured proportions of timber in the walls. We have pictured here the likely heat gains above this zero line and the heat losses below. The brown heat gain is the amount of heating energy that we buy. The red-orange color above it is the amount of solar gain in through the windows. We've accounted for the heat gain from people and lights and appliances at the tops of these bars. The first two parts of the bar below the middle zero line are the heat loss due to air leakage first and due to opening the windows for ventilation. Note, because the windows are large, we're actually opening them to get rid of the solar heat even in winter. The square box shows the heat losses conducted through the roof, floors, wall, and windows. The complexity of this graph is increased by the fact that we have two energy balance bars for each month. The left-hand bar is the specified building performance with the lower amount of timber on the walls. On the right, the as-built. If you look carefully in the circled area, you can see that the model is indeed accounting for the extra thermal bridging in the walls, and thus the larger heat loss in the as-built building. But the really odd thing for us was that these overall energy performance figures that are shown at the top of the page are unexpectedly worse for the as specified building with the better R value in the walls. If you just looked at the total energy use at the top of the page, the energy performance of the building seems to be breaking the laws of physics. The reality in the detail in this circle is suggesting it's how we're operating the windows, the behavior of the people, that is making the difference. It would be remiss of me at this point not to highlight the dilemma documented by Lauren Christie talking to consumers back in the early 2000s about their house purchase decisions. She identified a serious issue about the disconnect between homeowners' desire to act sustainably and their actions. Homeowners understood the value to them of the energy efficiency or low carbon options they had, but would not choose them unless everyone else did so. To this market perversity, I would add Herman Molina's research, where it is becoming clear house buyers are looking for very different comfort performance than designers typically intend, and they also don't trust vendors or vendors' agents at all. What I've learned from this and the other studies is that detailed performance pictures are far more important than simplistic calculations. Even improved monthly heat balance calculators like BHPP or ALF, which allow for solar gains as well as heat losses and thermal bridges, do not help look at anything other than energy. Convention suggests designers want simplistic rule of thumb calculations because they make the design decisions made in the early hours and days of a design concept easily. Clearly, these rules of thumbs mislead. These research efforts lead to the types of lessons listed here. Energy performance certificates, however calculated, enable standardized comparisons. They're not related to how people will actually use a building. They don't tell us what it's like to live in that building. Even if you measure the actual temperatures in a building or the energy use, you get no information about livability unless you measure 1, the temperature that was delivered as a result of 2, the energy use, and 3, unless you also talk to the people about how they're using the building, you have no way of knowing how well the building is actually performing. We must be looking at what people really want inside the buildings. It's not some magic 18 degrees Celsius minimum temperature. It's a much richer and more complex issue than that. In drawing this to a close, I'd like to present here my collaborators, my colleagues, and just one example of how this theme has developed in my research. I long ago determined that we need to develop a way of sketching the detailed performance of a building with the same qualitative richness as an architect's sketch. Rules of thumb don't do this. We're aiming to provide a rich picture of what it would be like to live, work, or play in a building early in design. Not prediction of how people will run a building, that would be insane. Rather, very early in the design process, when most of the important decisions are made, providing data so that potential building users can understand how the building might work for them. A simplistic rule of thumb merely tells us about the building properties. On the topic of PhD students, I'd like to conclude by referencing the shoulders I've stood on that have enabled this think piece. My academic colleagues, that is the staff, PhD and master's students at the Wellington School of Architecture. They keep me intellectually challenged and stimulated. The list here is indicative of the framework of research I'm involved in, and ultimately are the reason for the People and Buildings title. What I realized in putting this together is the students that I'm currently supervising for PhD are mostly focusing on different aspects of this livability issue. They're talking to people, understanding the important things about how we use and design our buildings and environments they create. Thank you for your attention. I look forward to the questions.